Bismillahirrahmanirrahim. Welcome everybody. Today we are going to start the next topic of the chapter solids, and that is the crystal lattice and unit cells. It is one of the most important topics of the chapter of solids. So I will recommend you to listen it very carefully and completely. First of all, let us discuss what is meant by the crystal lattice. A crystal lattice may also be called as the space lattice, or simply it can be called as the lattice. Now, how can we define the crystal lattice? The regular arrangement of constituent particles. We know that in crystalline solid there is regular arrangement of the particles, and that regular arrangement of the constituent particles. Now, the constituent particles may be atoms, ions, or molecules of a crystalline substance in space. In space mean in three dimensions. So that regular pattern, that regular arrangement of the atoms, ions or molecules in three dimensions is called as space lattice, crystal lattice, or simply it may be called as the lattice. Now this one is a space lattice in front of you. Here it is very simple to draw. It is not much difficult to draw. I will make a video lecture on it, how to draw this crystal lattice, or it will be explained well in the structure of NaCl. So this one is a crystal lattice in which the particles are regularly arranged. Now these particles which are shown with the black bold dots, red bold dots, these are called as the lattice points or lattice sites. And these lattice points or lattice sites actually represent the constituent particles, that may be atoms, ions, or molecules. And keep in mind that these lattice sites are either represented by bold dots or simply by circles. Simply by circle mean you can draw this in this fashion. So these lattice points or lattice sites are the points having the minimum potential energy. Mean the atoms, ions or molecules occupy those positions in the crystal lattice where they have the minimum potential energy and maximum stability. Now this crystal lattice has certain characteristics. The first one is that all the lattice points or lattice sites in this crystal lattice, they have same environment, same chemical environment, means their surroundings, their environment, they are same. So their position is different, but their environment is same, mean they are just alike, they are identical to each other. The second point is every particle is represented by lattice point irrespective of its nature, mean all the constituent particles irrespective of their nature. What does it mean? It means whether the particles are atoms, ions or molecules, they will be represented by these points. So it is not the like if the atoms are there then these are the points, and if the ions are there then these points are replaced by something else, and in case of molecules these points are not points but they are crosses actually. No, all particles whether they are atoms, molecules or ions, they will be shown like this, like these bold dots are like the circles. So all are represented in the same manner. The third one and the very important one, that a crystal lattice is basically made of repeating units, and those repeating units are called as the unit cells. It is just like if you consider your body as a crystal lattice, then the cells are the unit cells, and the repetition of the cells makes your body. In the same way, the repetition of the unit cell makes the crystal lattice. Now, there is another example that if you take wall as a crystal lattice, then the bricks are the repeating units, and those bricks are actually the lattice points or lattice sites. Sorry, those bricks are actually the unit cells. So unit cell is the simplest part of a crystal lattice, and when these unit cells are stacked together, they are collected together, then the crystal lattice is produced. So this crystal lattice also consists of the unit cells. And now, what is meant by unit cell? Let us first define the unit cell. Unit cell is actually the simplest part of a crystal that has all the characteristics of the entire crystal. So, unit cell is the smallest repeating unit of a crystal lattice, which shows all the characteristics of a crystal. Just like you know that every cell of your body that has full characteristics of the life, and every cell is a representative of life. In the same way, every unit cell is the representative of the crystal lattice. It shows the symmetry of the crystal lattice. It shows the size of the crystal lattice. So that unit cell is basically the smallest representative of the crystal lattice. Now I have made a simple cubic unit cell here. Out of all the unit cell, the simplest unit cell is the cubic. Now this one is the cubic unit cell. It has three axes. One is x-axis, second is y-axis, and third is z-axis. So first of all, it should be quite clear to you that unit cell is also a three-dimensional entity. The unit cell is not two-dimensional. It is also three-dimensional. It has three axes. So it is also a three-dimensional smallest part of the crystal lattice. Now the edge length, this is the origin from this point to this point. This is an edge length and it is shown by the small letter a. Keep in mind that the edge length along x-axis will be shown with the small a. You cannot replace this a with b or c. This is fixed that the edge length of the x-axis will be called as the a. Similarly, the edge length of the y-axis that will be called or that will be shown with the letter b. The edge length of the z-axis up to this that will be shown with the small c. So A, B, C, these are the three edge lengths along x-axis, y-axis and z-axis respectively. In the same way, there are three interfacial angles. This one is a complete face. This one. Similarly, this is also a complete face. This one is also a complete face. A cube has six faces, and the angle between these faces they are called as the interfacial angles. If you are sitting in a room, you can see that it has six faces. One at the front of you, second at the back of you, third right one, fourth left one, fifth the upper one, that is the roof, and sixth the floor. So every cube has actually six faces. And the angle between these faces is called as the interfacial angle. Now the angle between x-axis and y-axis that is fixed and it will be called as gamma. You cannot call it as alpha or beta because it will remain gamma. In crystallographic we give certain angles to the certain axis and they remain fixed. Similarly, the interfacial angle between y and z that is called as the alpha and the interfacial angle between z and x that is called as the beta. So a unit cell is actually represented by the six parameters, out of which three are the bond lengths ABC and three are the interfacial angles alpha, beta and gamma. And these six parameters are collectively called as the crystallographic elements, or you can also call it as the unit cell dimensions. And depending upon the relationship between these unit cell dimensions A, B, C, alpha, beta and gamma, there are seven types of the unit cells. Crystallography is actually the branch in which we study the structure of the crystals. And a very important technique, X-ray diffraction, that helps us to study the structure of the different crystals. Now, depending upon these parameters, there are how many types of the unit cells? Seven types. So let us discuss now the types of the unit cells one by one. The first unit cell is cubic or cube. Now let us draw a cube. It is simple to draw it. It is something like this. This one is a cube. In case of a cube, what is the relationship between the crystallographic elements? All three edge lengths they are equal, and all three angles they are also equal, and they are equal to 90 degree. And when the cubes are collected, then the cubic crystal lattice is produced. And the examples of the cubic crystal lattice are the coinage metals like iron, copper, silver, and gold. They have all cubic crystal lattice. Similarly, diamond has cubic crystal lattice, and the common salt NaCl that has also the cubic crystal lattice. Now listen very carefully from now. This cube is a unit cell, and there are four types of the cube. Very carefully, I will recommend you to listen very carefully. There are four types of the cube. In the first type, the lattice points, or you can say atoms, molecules, or ions, they only occupy the corners of the cube. Mean a cube that has the lattice points, lattice sides, or you may say constituent particles only at the eight corners. That is called as the simple cube or primitive cube. So this one is the simple or primitive cube. The next type of the cube is in which in the next type of the cube the lattice points are present at eight corners, but another lattice point is present at the center of the body. Now this is called as the body centered cube, and all these points they are connected to this center. Like this, something like this. So this is the body centered cube. So one is the simple cube or primitive cube, second is the body centered cube. Now let us talk about the third type. The third type of the cube is that cube in which constituent particles are present at the corner, and also there are two constituent particles which are present at the center of the opposite faces. And usually those opposite faces are the top one and the bottom one, like this. This one. Now what type of cube it is? It is the third type, which is called as end centered cube. And now the fourth one. In the fourth type, the lattice points are present at the corner of the cube, and also one lattice point is present at the center of the each face. This one is at the above face, below, in the right, left, center of the back, and this one is on the center of the front. Now this cube, that is called as the face centered cube. So the fourth type is the face centered cube. Cube is a unit cell having these relationship, and there are four types of the cube. Simple or primitive cube having lattice points only at the eight corners. Body centered cube having at least 9 identical points, 8 at the corners, 1 at the center of the body. End centered cube having at least 10 identical points, 8 at the corners and 2 at the center of the two opposite faces, usually above and below. and face-centered cube in which at least 14 identical lattice points are seen. 8 are present at the corners and 6 are present at the center of the each face of the cube. And these four types of the cube, they are called as its Bravais lattices. Now keep one thing in your mind, that a crystal which will be made with the face-centered cubic type of the cube, that will be face-centered cubic crystal lattice. And a crystal lattice that will consist of the body-centered cube, that will be called as the body-centered cubic crystal lattice. So there are four types of the crystal lattice if they consist of the cubes. But in one crystal lattice, there will be only one type. It is not the case that a crystal lattice has all these four types. No. One crystal lattice is made up of only one kind of the cubes. So this was the first unit cell, that is the cubic. Now let us talk about the second type. And that is tetragonal. In case of the tetragonal unit cell, the relationship between the crystallographic elements is A is equal to B, but B is not equal to C. Mean the edge length on the x-axis, that is equal to the edge length of the y-axis, but these two are different from edge length of the z-axis. And in case of angles, alpha is equal to beta is equal to gamma, and they are equal to 90 degree. Angles are all same and they are at right angle to each other. Mean the angle is 90 degree. Now I am going to tell you how to draw this tetragonal shape. Listen very carefully and watch it please. You are going to draw a rectangle first. And now draw another rectangle inside this, like this. Okay. Now join them. This is the tetragonal unit cell. Now in this case of the tetragonal unit cell, there are two Bravais lattices. It is of two types. One is the body centered and other is the simple. Now let us draw these two. What will be the body centered? In case of body centered, there will be one lattice point at each corner and the same lattice point will be present at the center of the body. This one will be the body centered tetragonal Bravais lattice. And second one is the simple. In case of simple, there are points only at the corners. So this in front of you, that is an example of the tetragonal unit cell. This one is the tetragonal unit cell actually. The cube has 4 Bravais lattices and the tetragonal unit cell has 2 Bravais lattices. So total of the Bravais lattices are equal to 6 and total unit cells that we have discussed so far, they are 2. Now let us move now towards the third one. That is the orthorhombic. What is the relationship between the crystallographic elements in the orthorhombic? In this case, A is not equal to B and B is not equal to C. So one thing is clear, that all the edge lengths, they are different from each other. But angles, again they are equal and they are equal to 90 degree. Mean they are at the right angle to each other. Now I am going to tell you how to draw this orthorhombic. Look at this please. Make a rectangle first. Then make another rectangle starting from almost the center of this one. So this one is the second rectangle. Now connect these two. Their size should be equal. And this one is the orthorhombic type of unit cell. Now, how many Bravais lattices this orthorhombic type has? It has 4 Bravais lattices. What are those 4? One is the simple, second is the body centered, third is the end centered, and fourth one is the face centered. I have already explained these in detail, but I am repeating this, that in case of simple, there will be lattice points only at corners. In case of body centered, there will be one point at the center of the body as well. In case of end centered, each two opposite faces, any two opposite faces that have one point at their center. And in case of face centered cube, every face will be having one point at the center of it. So, cubic unit cell, tetragonal unit cell, orthorhombic. These are the 3 types of the unit cell. Now let us calculate their Bravais lattices. 4 of the cube, 2 of the tetragonal, and 4 of the orthorhombic. So total are 10. So these 3 unit cell have 10 Bravais lattices. Now let us move towards the 4th type, and that is the monoclinic. Now what is the relationship between the crystallographic elements? A is not equal to B and B is not equal to C. And what is the relationship between angles? Alpha is equal to gamma is equal to 90, but beta is not equal to 90. So this angle will not be equal to 90, while these two, they will be equal to the 90 degree. There are so many examples of the monoclinic as well, like the tetragonal crystal. The example is tin oxide, manganese dioxide, ammonium bromide, etc. Like in case of orthorhombic, you know, rhombic sulfur, that is very common. Iodine has orthorhombic type of crystal. And monoclinic, sulfur, sugar, borax, these are the examples of the monoclinic lattice. Now listen very carefully and watch it, how to draw this monoclinic type. So first of all, again make a rectangle, and then make another rectangle outside this rectangle like this, and match these two. Now this one is the type of the monoclinic unit cell. Now how many Bravais lattices this monoclinic has? It has 2 Bravais lattices. Simple. It has 2 types, mean one is the simple and other is the end centered. So simple has lattice points only at the corner, and end centered has lattice point at the corners as well as at the center of the 2 opposite faces. Now this one is the 4th unit cell, and now the total number of Bravais lattices, they are 12. Let us move towards the next one. That is the fifth, and it is hexagonal. Now, what is the relationship between these? A is equal to B, but B is not equal to C. So A is equal to B and B is not equal to C. Mean the edge length of x-axis and y-axis are equal, but that of the z-axis, that is unequal. And what is the relationship between angles? Alpha is equal to beta is equal to 90 degree, but gamma is equal to 120 degree. And all of us, we know that in hexagonal structure, one of the angle is 120 degree. Now, how to draw this? It is very simple to draw. Draw a hexagon like this. There should be two lines here, and again two lines. Join them. So this one is the hexagonal type. And in this hexagonal type, this angle is 90 degree. This angle is also 90 degree. These are alpha and beta. But here is the gamma, which is equal to 120 degree. And the example of the hexagonal crystals are one of the very famous example that you know is graphite. Similarly, ice is an example of the hexagonal crystals, and zinc oxide, cadmium sulfide, etc. These are the examples of the hexagonal form. Now the hexagonal form has only one Bravais lattice, and that is the simple one. So now they have become 13. Let us move towards the sixth one. The sixth is rhombohedral or trigonal. Now, what is the relationship between the crystallographic elements? A is equal to B is equal to C. Mean all edge lengths they are equal, and alpha is equal to beta is equal to gamma, but they are slightly greater than 90 degree. So this one is the relationship of the crystallographic elements. Now how to draw this one? Simply make a slightly curved or slightly unsymmetrical cube. And this one will be the example of the rhombohedral unit cell. It is just like a cube, but it will be slightly, you can say at one side, or it will not be just like this perfect cube, slightly unsymmetrical cube, because the angles they are not perfectly 90 degree, they are slightly greater than the 90 degree. The example of the rhombohedral crystals are bismuth, aluminium oxide, sodium nitrate, and potassium nitrate, etc. How many Bravais lattice it has? It has only one Bravais lattice. That is simple. Mean again all the lattice point they will just occupying the corners of the unit cell. Now let us move towards the last one, seventh, and that is the triclinic. In case of triclinic, A is not equal to B, B is not equal to C. So all the edge lengths they are different from each other. And similarly, alpha is not equal to beta, is not equal to gamma, is not equal to 90 degree. So all bond angles they are also different from the each other. How to draw this one? So make a rectangle, but that rectangle should be not a symmetrical one. And then make another rectangle like this and join them. So this one is the example of the this one is the triclinic unit cell. How many Bravais lattices it has? It has only one Bravais lattice, and that is the simple. Now these are the 7 types of the unit cells. There are so many crystals which are triclinic. I can tell you that copper sulfate pentahydrate, similarly potassium dichromate and boric acid. These are the examples of the triclinic system. Now, how many unit cells are there? Cubic, tetragonal, orthorhombic, monoclinic, hexagonal, rhombohedral, triclinic. There are 7 types of the unit cell. But if you will calculate their Bravais lattices, you will see that I have told you there are 15 total. But in case of cube, the simple cube is the primitive type. So in case of cube, we consider only 3 Bravais lattices. One is face-centered cubic, second is end-centered cubic, and third is the body-centered cubic. The primitive is considered out of it. So there are 3 Bravais lattices of the cube. Similarly, 2 Bravais lattices of the tetragonal, 4 of the orthorhombic, 2 monoclinic, 1 hexagonal, 1 rhombohedral, and 1 triclinic. And when you will add all these, they will be 14. So total unit cells are of 7 types, and total Bravais lattices are of 14 types. Now the concept of the unit cells crystal lattice, that is very important to understand, because we are going to discuss in the next lecture, we are going to discuss the properties of the crystalline solid, and in those properties during isomorphism, polymorphism, especially during habit of the crystal, we are going to say all these terms. So you must have an idea of these crystal lattice unit cell types and their Bravais lattices if you want to completely understand the concept of the isomorphism, polymorphism, transition temperature, allotropy, and especially the habit of the crystal. So that was all about the crystal lattice and the type of the unit cell. Next time, inshallah, we will come up with the properties of the crystalline solid. Till then, Allah Hafiz.